Hi again, guys. So Tuesday today, and as promised, I am making another video. That will be about the fundamentals of EEG and FNIRS. I saw that most of you have watched the first video. I really hope you find them useful, interesting, not too complicated, but enough challenging to make you look into whatever is interesting for you more, and also, help you towards your common problem project. So again, after yesterday talking about very basics that have to do with action perception and why sports neuroscience exists and why sports neuroscience is so interested in athletes and how their brain works. Today, we're going to talk about two ways mainly that we can use to measure activity that happens in our brain. Okay, we're going to go through the basics. I'm going to try to break down the information as much as possible. I promise I didn't do it in the first video. I won't do it in any video. I'm not going too deep. Right? I'm just giving you enough information that has to do with sports neuroscience, and for all the reasons that I mentioned like 2 minutes ago. We're going to keep listening to some cool house music. So you're welcome again. And let's talk a little bit about our second chapter today, fundamentals of electroencephalopathy, pretty long word, and optical imaging. Okay, so EEG and mainly concerning optical imaging, we'll talk about functional near infrared spectrometry, FNIRS. A lot of long words today, but chill, we'll be fine. All right. Okay. I always put some comments as well under the video. I don't know if you noticed, so you can go over them because that's the baseline, the outline of what I'm covering. And again, I have my notes so I don't forget everything I want to say. So our brain is a remarkable organ, okay, and it has that ability. Now that's why it's remarkable. One of the reasons to learn and to capitalize from experience, which is very important if you think about sports performance, peak performance in anything, but for us, for sports performance, right? So when there is a meaningful event happening around us, whatever that is, and whatever is meaningful for you or me or whoever, right? There is a lot of physiological events that happen in our body, heart rate, hormones, whatever is going on. A lot of physiological events in our body but they're all related to our brain. How? We talked about that in class. We have neural connection, neural structures that have those electrochemical connections, right? And I've talked about in class. We talked about it, about the action potentials and the post-synaptic potentials. And I don't know if you remember, we have the excitatory versus the inhibitory signals. Remember, and those kind of compete with each other. But then at the end, the summation of all these signals create that post-synaptic potential that I just said, that produces that activity that we see in our brain, electrophysiological activity, which can be captured by some electromagnetic methods, CEG, CF, and IRS. Okay, that's it. Now, a cool term that I would like you to know is neurovascular coupling, and that has to do with F and IRS. Has to do with the fact that when we have changes in neuroactivity, we also have changes in regional cerebral blood flow. So the difference is when our neurons are firing in our brain, there is neural activity, the blood flow changes in our brain, and that we'll see in a little bit why is that important and why we're trying to measure that and what we understand through that. Okay, neurovascular coupling. All right, let's keep going. We study class that we have the action potentials and we have the postsynaptic potentials. EEG supposedly it can measure the PSP, the postsynaptic potential, not the AP. The AP is too fast or too short in duration for the EEG to capture it. So the EEG captures PSP, and that's how we do this measurement. In order to be able to capture that information, that activity, we need, as you will see in the notes, we need a large population of neurons firing at the same time, so synchronous activity, right? And then those neurons have to be arranged in a specific way consistently so the EEG can capture that. Cool? Now, we can capture that activity based on frequency. We measure it in hertz, right? And you will see we have alpha, beta, theta, delta, and bands. So based on what we can just pick one band if we want to, right? Based on the, as I said, on the frequency, which is measured in hertz, or based on time. And we have done a project like this here, and some of you have participated in Kyle Pellerin presented it, ACSM, original ACSM, right? I had to do based on time. That's called event-related potential, ERP. So in this one, we may measure any frequency, but we change something, so we may have some kind of stages. In our case, we change the intensity on the bike. So we try to see how the frequency changed based on the intensity. But we measure any frequency. Does that make sense? I hope so. Now, optical imaging. This one will go back to the neurovascular coupling that I talked about, because we can track and measure oxygenated and deoxygenated hemoglobin. I hope you know what hemoglobin is, right? Up to this point. And that has to do with light and how we capture light through chromophores. That's the basic idea. So it's very popular. FNIRS is very popular and is based on NIR, near infrared light. So by using NIR, we can distinguish when we have goes through. We can distinguish between oxygenated, deoxygenated hemoglobin, water, and lipids. So after all, if we can do that, we can talk about the concentration, total concentration of hemoglobin, and break it down in oxygenated and deoxygenated in real time, and that's pretty amazing, right? So that's what optical imaging does. That has to do with blood flow and oxygen concentration, okay? EEG has to do with bands of the frequency of all that activity that happens in our brains. We are measuring activity in the brain, but different kind of activity. We cool? All right, let's keep going. Let's compare them. In general, again, we're not going to go into detail. EEG is not very good when we're talking about spatial resolution to detect exactly where the frequency, the signal is coming from. It's really hard. We can't. It has limited ability to do that up to now, right? It is better when we talk about time because it captures it faster. It doesn't have that delay. So when we talk about time resolution, EEG is pretty good. FNIRS is good too, but near infrared is good too. But the EEG is a little bit better. Now, when we talk about spatial resolution, near infrared is better than EEG. Okay, EEG doesn't have that localization power. So EEG doesn't have that localization power when FNIRS signal is delayed. So again, time resolution, EEG, that will be our best bet. Spatial resolution, near infrared resolution, FNIRS. Okay. Now we're done with the first part. Second part, let's talk a little bit more about EEG in sport and exercise. Alpha band is very, very popular. So most of the research if you find out there or will be in your project, most likely is about alpha band. When we talk about clinical or rehabilitation use, it's very common and most common in concussions. And some of you have projects with concussions, okay? So most likely to talk about EEG. The manifestation, the clinical manifestations, the individual clinical manifestation may vary. So it's different to have a general idea of what to expect when we do EEG with somebody who has suffered concussion. However, in general, we see alpha activity to go down and the ratio between theta and alpha power to go up. That's something that is kind of common. One more thing that I want you to remember is the P300, which is a positive kind of response that happens 300 milliseconds or later after the initiation of the stimulus. Okay, and because it is related to allocation of attention resources, to attention, it's very interesting because it has been shown that people who suffer concussions, and actually way later after they suffered it, they have a decrease in the activation of P300 or the number of P300s. Now, research lines that have to do with EEG, the things that I do too, I'm looking for biomarkers of performance. I'm trying to see how the brain of the athlete is different from the non-athlete or the expert from the novice. And in the project that we did it with intensity to see how a group of athletes reacts. Other people look for different things. The basic idea is biomarkers of performance. Everybody's looking for that. Not easy to find out. Some correlates. We know that experts have lower alpha activity during preparing and during focusing on an activity. The hypothesis behind it is because they already know so well the activity, right? The activation is lower than in others. What else? Okay. And I'm not going to go into detail concerning physical exercise. There is a lot of research on heat, less on space that has to do with gravity, have to do with astronauts and so on and so forth. But the basic idea here that we need to remember is that heat and gravity affect the function of the brain, and that's very interesting to see what's happening when we are exercising or there's this physical activity under those conditions. Alright, third part, FNRS in sport. Mainly we talk about, we use it for oxygenation of muscle or metabolism, oxidative energy metabolism. And as we see in our notes, the usage has been increased because it's more portable, it costs less, it's barely invasive, right? And we can use it during activity. Something that is not so easy with EEG because when you move there's noise. So yeah, we'll talk about that in a little bit. Clinical rehabilitation applications, not very popular. In traumatic injury, brain traumatic injury has been found promising. We don't have a lot of data, and also it has been used in conjunction with virtual reality, and it doesn't affect in a negative way. So FNIRS and virtual reality devices have been used together, and we have some preliminary data there that's very, very promising. Research, very limited in sports. We have research because it is easy to do it, as we said, in activity while people were walking or running on a treadmill. It has helped with again proving that fatigue is a complex phenomenon, and it's not just fatigue of the muscle, it has to do with the nervous system as well. And again, because through FNIRS we can detect how where a decrease or increases of oxygenated and deoxygenated hemoglobin, that's another indication that fatigue is not as simple as a phenomenon as we thought. All right, and we talked about that in class, if you remember. One more thing we know is that the higher the level of expertise, the less the cortical activity, okay, that we capture with FNIRS, which again may show that less activity we have because it's easier for an expert, so we have more economy, okay, of the resources that we have to use. Fourth part and last part. Let's compare and contrast them a little bit, right? First of all, both rely on sensors, and those sensors are going to be put on the scalp. Okay, they can be put individually, or usually they have that cap you've seen, they're already fixed, and you put it on you. All right. Let's talk a little bit about placement. We have some landmark points. Excuse me. So we have measuring, which is right in front of your eye, right here. Okay. Inion, which is if you go straight line, you go through my ear, it's right back here, right? Measuring here, and we have inion here, and then right here we have the left preauricular, and on the other side we'll have the right one. Some landmark points, and I understand them a little bit. And then we'll have letters, and I explain the details. O means occipital, and F means frontal, so that indicates the positioning. Another way to indicate positioning. We can have mixed labels, FT or FP or F, whatever. So, and then we can add numbers to it. So there is a specific way to address where we put its sensor. So if you have an even number, it will be on the right hemisphere, and if you have an odd number, it will be on the left hemisphere. So F4 and F5, for somebody who knows EG, he knows exactly, or she knows exactly what we're looking, where we're putting that sensor. Does it make sense? That's all I need you to know. Z has to do with the midline, right in the middle. What else? I'm not going to talk about the diffuse systems in this video, but there are different ways to put them. That has to do with how many and the distance in between them, and so on and so forth. Just know there are letters, there are numbers, and those can be combined in a way that we know exactly where F4 is, for example. The positioning of the sensor on the scalp. That's it. Preparation. We usually, lately there are other ones without gel, but we put gel through the sensor, so we have some kind of connection between the scalp and the sensor. You don't want the impedance value to be above 5 kilo ohm, because it's 5 kilo ohm or above. Kilo ohm is a way to measure electrical resistance. So you put enough gel so that impedance be below 5 kilo ohm. But then again, if you put too much to this one and then to the next one, we may have bridging, meaning the gel are connecting, and then there is some kind of they're not functioning very well because those two signals are connecting through the gel. We put too much. So it's a little bit of technical how to place the electrodes and how to make them work and make sure every each one of them works and gives you less than 5 kilo ohm. Okay. Now we also have two more things I would like to talk about right now. We have a ground sensor that is for safety, right? And we also have reference sensors that are for computational, so to compare and contrast. And this one, for example, for us it was earlobe, right? For this one was the reference, and then every other signal was compared to that one. So the ground one was just safety and hopefully lowering noise, okay? But the reference is just for computational reasons, as we are collecting the data. Recording, we need to understand, we need to figure out in how much of data are we going to save. Also, there are specific filters that can decrease the noise, and all these are predetermined, or we can determine them, and they happen while we are recording. Okay. Now, what's happening when we wanna analyze the data? So now here we're gonna break it down into the EEG first, and then last FNIRS, and then we're done. So the main idea is here we can refilter the whole signal when it's offline, right, and clean it. How do we do that? Bandpass filters. So we have cutoff frequencies. So from here to there, everything below or above, it's out. Okay, that's one thing. Lately, more and more we use artifacts correction algorithms that find some artifacts, noise, okay, and just make computations and take it out or fix it. And then we break down the data. Is it time domain? Or is it frequency domain? If it's time domain like hours, you can break it down into block, like the first 2 minutes and then the 30 minutes, and you analyze them per whatever period of time. If it's frequency domain, means you're looking for specific frequency, and most likely you change what I was doing. So now I was looking this way, and then you look that way, and you want to see by me changing whatever whatever you were showing me how alpha frequency changed, right? So again, that will be based on the frequency domain and what happened alpha waves. It has to do with the task mainly. For us, that was the time domain. It wasn't about the task. It was about the same frequency, but we just changed at the same task something. And we wanted to see what happened after the third minute, the second minute, what happened during warm-up, what happened during cool-down with the intensity. Okay? I hope that makes sense. FNIRS, again, bandpass filters. We remove artifacts, and at the very, very end, we convert the signal to something that we can read and figure out what's going on with the hemoglobin. That's pretty much it, guys. I hope that was useful, and I hope you like these videos more than just PowerPoint slideshows. I decided to do it that way. It may be a little bit more work for me, but hope you enjoy it. I really hope you enjoy it. Enjoy the day for me as well. If you're here in Plattsburgh, it's pretty sunny outside. Stay safe, and don't forget, lift intentionally, not habitually. Okay, don't allow this thing that's happening right now to make you lose all your muscle gains. Okay. All right, guys. I'll see you again. I'll send you my next video next week.